Hello everybody, welcome back to another strengths materials video. This one's going to be on critical buckling load once again, but for built up columns. And the only change with these separate problems is that you're going to have to consider the parallel axis theorem. If you need a recall on how to do that, you can click the link up top here. But I'll explain all the basics that you need for solving this problem here, which goes as follows. We have a column that's constructed using four A992 steel angles, that's these blue ones right here, and they're laced together with these gray elements here. The length of the column is 25 feet and it's pin. So that's going to be for our KL value. And each angle is shown to have the following geometric properties. So it gives you the area of each angle and the moment of inertia about X and Y. And that value is the same, meaning that the length of each leg is the same as well. Now, also to determine the D between the centroids C of the angle so the column can support an axial load of 350 kip without buckling. It asks us to neglect the effect of lacing. Why does it ask us to neglect that? Simply just to make the problem easier, because these plates would actually be adding to the total moment of inertia of the column. But what is this problem asking for in the first place? It's asking for this distance d. And it's telling us that as you shift these angles, you're going to be creating a larger distance d between respective centroids. And what does that mean? That means that as you increase this d value, you're going to be increasing the total moment of inertia of your column. So what is the point of that? What's the takeaway? The takeaway is that there is a specific moment of inertia value, a minimum moment of inertia, that will allow a maximum axial load of 350 kip based on this critical buckling load formula right here. So if we plugged in 350 into this formula, then we could back calculate what moment of inertia of the total composite column would be required in order to satisfy that load allowance. And this inertia value will be dictated by what? The parallel axis theorem. And in this theorem, you have this d value, which once again is the unknown in this problem. So now we can finally start solving. We have a game plan. We start with the inertia, solve for the global moment of inertia, and then plug that back into this formula to get that d value. Okay. So we'll start first with Ix, which is the global moment of inertia of the column, which will equal to Iy because this is symmetric about both axes. Okay. And I'm going to start off with the reference at the center because Ix and Iy be able to use the same formula in order to solve for the global moment of inertia for both axes. Okay. So that means we have what? We have Ix prime, which is simply the local moment of inertia for each angle. We have four angles in the problem, so this whole formula is going to end up being multiplied by 4. We have that inertia value right here given to us, 2.22 for each column, or for each angle, sorry, plus the area of each column, for each angle, I'm so sorry, very tired today, 2.75. And then we have this dy value or this dx value, depending on whatever the reference is. But that is simply going to be from the centroid of the column or that reference axis that we've chosen to the centroid of each of these angles. And that value is simply going to be d over 2. So plugging that in, you square it. That total thing will be inches to the 4, just based on the units of inertia. And solving for this, you're going to be left with a equation with an unknown variable. So you have 8.88 plus 2.75 d squared. Now we can go ahead with another quick check before we hop into the main part of the problem. We just need to make sure that these formulas for Euler are applicable. And to make sure they are applicable, we have to make sure that the critical stress is less than the yield stress of the steel, because the critical buckling failure happens during the elastic phase of loading. Okay, so if we say that the critical load is equal to the critical axial load over the total area of the column, we will have something that looks like this. We have 350 times 10 to the 3, that'll be pounds, and that'll be over the total area. So we have 4 angles, so 4 times 2.75, and that'll be inches squared. Solving for that, you'll be left with 31.8 times 10 to the 3 psi, which is less than the yield stress up here, 38 times 10 to the 3 psi. So that's good. That means we can move on to the final part of the problem, which is simply back solving for this d value in the I of this formula. So plugging into this formula down here, we would have something that looks like this. And then solving for all that, you are actually going to be able to get this d value that we were looking for earlier, and that's simply going to be equal to 6.07 inches. And you can review this formula and how I kind of worked to get this d isolated by checking this out right here. And just as another check for this formula, we already have the d value, but let's make sure we have enough length on this leg in order to put a lacing member between them. So in order to ensure that, we need to make sure that this value is greater than 2 times the length of the distance of the legs between the centroids. So we have 2 times 2.068, and that is equal to 4.136 inches, which is greater than 6.07 inches, meaning that you would have about a 2-inch gap between the ends of each of these legs. Okay, so that's the whole problem. That's your final answer right over here. And I hope this helped to kind of understand what's going on with composite columns and how to use that parallel axis theorem again for these type of formulas.